I love the PS2. When I was a kid, I would spend every summer in the countryside with no internet. The only form of entertainment me and my cousins had, besides punching each other for fun, was an old PlayStation 2 with a box of pirated games. That rusty console basically raised me, but back then I had no idea how it actually worked. So now, as a computer science student, I finally wanted to understand it. I remade the entire PS2 in 3D to examine its workflow, from how it read games to how it handled massive 3D worlds and turn them into a 2D image on your TV. And by the end, I'll finally figure out if the PS2 truly was this god-tier piece of hardware or if I'm just a hopelessly nostalgic caveman. The first piece of the puzzle, games, and specifically the discs they came on, an ancient technology known as a DVD. In hindsight, looking back at the early 2000s, running your games off of DVDs doesn't seem that much more impressive than just using CDs. I mean, they're both just spinning plastic discs, right? How big of a difference could there really be? Turns out, a pretty big one. Aside from the obvious fact that DVDs had more storage space, which meant higher resolution textures and more detailed models, DVDs had much higher data transfer speeds. And when your entire game is being read in real time off of a spinning piece of plastic, you'll take any advantage you can get. I'm gonna take a wild guess here and assume you know how CDs work. If not, that's fine, I'm gonna explain it anyway. Every CD stores data as tiny pits and flat areas that reflect light differently. As the laser scans them, the reader detects changes in reflection over time and converts those changes into binary ones and zeros. Easy concept, right? Well, DVDs work the exact same way, the only difference is density. DVDs pack those grooves much closer together, resulting in much more data on the disc. And here's the clever part, higher density doesn't just mean more storage. Think, if we assume the disc spins the same speed, the laser is going to go over more data in the same time frame. Translation: just faster loading times. And that's a huge deal if you don't want loading screens every 30 seconds like on the PS1. Instead of dumping an entire level into memory up front like PS1, PS2 games could stream data continuously, pulling in textures, models, and animations on the fly as you moved through the world. That's how you got large environments and early open-world designs with minimal or completely hidden loading screens, despite the fact the PS2 only had 32 megabytes of RAM. But actually coordinating that data stream, total nightmare. It takes real computing power and it has to happen without getting in the way of the processor, which is already busy running physics, 3D math, and whatever terrible decisions the player is making. So the PS2's CPU had to work hand in hand with the disk drive without interfering with the main game logic. And that not bothering the main CPU part, huge deal for the PS2, because here's the plot twist, the PS2 was actually the weakest console of its entire generation. Well, at least clock speed wise. And yet, somehow this weak console still managed to outshine its competition in both visuals and performance. How? Magic? Witchcraft? Sony sacrificing the Dreamcast in a ritual circle? No, the truth is way simpler, but also somehow way nerdier. Enter the Emotion Engine, the PS2's secret weapon. It didn't beat other consoles through raw clock speed, but through a concept called parallelism. Instead of relying on one big chip doing everything, Sony packed the CPU with a bunch of specialized units that could work simultaneously, each handling its own turbocharged job. Thanks to PS2's parallel design, the main processor didn't have to stop and wait for data. While game logic ran on the main processor, a separate input-output processor handled more tedious tasks, like reading data from the disk and placing it into memory. From there, a dedicated DMA controller took over. Instead of the main processor copying data by hand, DMA moved large blocks of data automatically across the whole system at high speeds. Models, textures, and animation data could be streamed exactly where they were needed, feeding memory, graphics hardware, and coprocessors without stealing any precious computing power. But here's the thing, moving data efficiently was only half the job. Once that data arrived inside the Emotion Engine, something actually had to turn it into 3D worlds. And the real reason the PS2 could push so much geometry wasn't the CPU or the DMA controller, it was the vector units. To understand why vector units were so important, let me paint you a simple picture. Imagine a triangle. Each corner of that triangle is a point in 3D space, a vertex. Congrats, you now know what a polygon is. Now, take a bunch of those polygons, smash them together, and boom, you got 3D objects, environments, characters, entire worlds. And in order for those games to actually, have stuff moving around, we need to make those vertices move using math. And not the friendly kind, I'm talking matrices, vectors, and all kinds of transformations. And I know that sounds intimidating, but here's the only thing you need to understand. Vectors are just a way to store a vertex's coordinates. Basically a sticky note saying, hey, this is where I live in space. Matrices, they are just instructions that tell those vertices how to move. Multiply a matrix by a vector and suddenly your polygon has shifted, rotated, or stretched somewhere else. Imagine giving your friend very specific directions from their house to exactly where you'll meet. But your friend is a tiny point in space and the directions are math. Move 3 vertices and you move a polygon. And if you want the console to handle massive open worlds with tons of polygons and detailed models, it needs to be insanely fast at performing millions of these calculations every single frame. And that is where the PS2 truly shined. And the best part, all of this was happening in parallel. The vector units doing math, the DMA controller moving data, the CPU handling game logic, everyone doing their job at the same time instead of forming a sad little line and waiting their turn. This is exactly the reason the PS2 earned its reputation as a nightmare to develop for. In those first couple of years, studios were still trying to make games the old PS1 way. PS2's parallel design was basically like having a bunch of checkout lanes open, but devs only scanned items at one. The hardware itself had way more power, but developers just didn't know how to tap into it yet. But once devs finally wrapped their heads around the hardware tricks, the parallelism, the vector units, the DMA wizardry, the difference became undeniable. The PS2 went from a slightly shinier PS1 to something developers could actually rely on for ambitious projects. More polygons didn't just mean nicer looking models, they also opened the door for better particle effects, since those are basically tiny lightweight polygons with a bit of simulation sprinkled on top. Exactly the kind of workload the PS2 absolutely excelled at. And to turn all of those 3D polygons into a nice flat picture on your TV, the PS2 needed a super speedy helper, the Graphics Synthesizer, or GS. The CPU and the vector units did all the brainy stuff first, figuring out where every character and object was and how the world was laid out. Once the math nightmare was over, the DMA shoved all of those triangles to the GS in order to generate pixelated frames. To figure out what exactly ends up in one of those finished frames, games use something called camera space, which is just a pretentious way of saying virtual cameras. Remember when I said that every vertex has its own coordinates? Yeah, we are reusing those here. Those vertex positions get combined with the model's position, rotation, and scale, and then mixed again with the camera's own coordinates. At this point, let's say everything gets thrown into some magical mathematical blender. We don't need to know how it works exactly. The only important fact is that it uses a series of matrix transformations to project a vertex from a 3D scene onto a 2D plane. Do that for each vertex and eventually you get the projected version of the scene. Projected as in quote-unquote projected, because nothing is officially flat yet. This projection, still handled by the vector units by the way, just defines a sort of blueprint for rasterization, a process of turning all of those projected vertices into a true pixelated image. This part is handled by the GS, which goes polygon by polygon using each vertice's x and y coordinates to determine which pixels on the display that triangle takes up. To figure out which objects are in front of others, modern games usually use a third z-value or a depth buffer, which is basically per pixel information that tells the GPU which pixels are closer to the camera. This capability was very limited on the PS2 and only used sparingly. Instead, the PS2 relied on more primitive caveman-like tricks, like drawing triangles back to front, literally painting over previously rendered pixels to achieve depth. And finally, each polygon is shaded with a color or texture pre-assigned to that triangle. And yes, the coloring and shading only happens during rasterization, which means that every time you play a game, the 3D world is really just a bunch of colorless triangles, until they hit your TV as a colored 2D frame. This principle is basically how all games work, from old consoles like the PS2 to modern ones. What differs is how this task is handled. Modern consoles and PCs use something called shaders, tiny programs that run on the GPU to standardize the way polygons are transformed, shaded, and rasterized. Shaders provide a unified pipeline so games can run and be developed consistently across different hardware. The PS2 had none. Zero, not even baby shaders. And that's exactly the reason the PS2 relied so heavily on its parallel design, the vector units, the DMA controller, and arguably the most important, the graphics synthesizer. Because without shaders, the PS2 couldn't calculate complex lighting, reflections, shadows, or materials in real time. Instead, the developers had to fake it. They baked lighting directly into textures, layered transparent shapes to simulate shadows, and redrew parts of the image to mimic bloom and motion blur. The GS couldn't calculate real lighting per pixel, but it moved and blended pixels so fast that clever tricks made the world look alive anyway. All these tricks combined let the developers create some of the greatest games and franchises of all time. God of War, Metal Gear Solid, GTA, and so many more exist today because the PS2's hardware let developers dream and actually make those dreams happen. As biased as I may be, after spending thousands of hours in that countryside with the PS2, playing everything from the classics to the most unholy things ever burned onto a DVD, I still think it wasn't just nostalgia, it was a major stepping stone for what games are today. Truly one of the greatest consoles ever, and certainly my favorite of all time. You can grab my 3D model of the PS2 in the description for free as always. My subs know I only take likes and subs as payment, because apparently I don't value my work that much, and my negotiation skills peaked at age 12.